Okay, so we did this solving of the Laplace's equation in the upper half plane with this boundary data here, and we came with this formula here: u of xy is equal to 1 over pi times this integral. The integral is f of t times this function right here. This function is 1 over pi times y over x minus t squared plus y squared. This function here is called the Poisson kernel. Kernel is one of these weird words in math. In this context, it just means a function that you multiply another function by and integrate. And that's exactly what we're doing here. So that's why it's called the Poisson kernel. And this thing right here is typically called the Poisson extension of f to the upper half plane. Now, I'm going to make two claims about this. So first, here's a theorem. It says assume f is bounded and continuous. Okay, then, if u is defined like this, so u of xy equals 1 over pi times the integral t going from minus infinity to positive infinity, f of t y over x minus t squared plus y squared dt. If we define u this way, then two things are true. Then one, the Laplacian of u is equal to 0 on the upper half plane. UHP means the upper half plane. That's just where y is bigger than 0. And two, the limit as y goes to 0, really should say as y decreases to 0, of u of xy is equal to f of x. In this definition, y is positive, so the u we have defined is not technically defined on the real line, but what we can do is we can extend u to the real line by taking this limit here, and what this statement says is that if we do that, we recover the boundary function. Okay, so in other words, it is a solution to Laplace's equation in the upper half plane. Okay, now technically what we can do is we can pick some function. We can pick any function whose Laplace transform is equal to 0 on the upper half plane, and just redefine its values on the real line to be f of x, and that satisfies kind of, by the letter of the law, I guess, satisfies this equation. But it's not actually, we've just kind of, made something work that doesn't actually work. What this is saying is that the natural extension of u to the line, to the real line, gives you f of x, meaning it's continuous. Okay, so I'm only going to prove this part right here, but it's going to rely on a couple of things. So I'm going to spend a little bit of time here talking about this Poisson kernel. So the first thing that I want to mention, its shape is the following. So let's say we're going to graph it. This is the t-axis, and we want to graph something like this is the z-axis, and we want to graph the function z equals py of xt. Okay, well let's think about this. Let's think about the point x here. So let's say this is x. Notice that as t goes away from x, x minus t squared gets bigger. So as t goes away from x, the denominator gets bigger, so overall the Poisson kernel gets smaller. So we have a maximum here when t is equal to x. So we have a maximum when t is equal to x. It's an absolute maximum. And so it's an absolute maximum, and so therefore it's also a local maximum. So we have something like this. Notice also that it is symmetric about x. So it's like even about x. So if you look at x equals 0, that's an even function of t. But I say it's even about x, I mean we just shift it over to x and we get an even function. Even about x. Okay? And of course, as t goes to infinity, this goes to 0. And so we get something that looks roughly like this. Okay, so it kind of like has this same qualitative shape as a bell curve, but the normal distribution curve goes to 0 much faster. They kind of look alike. And this kind of looks like it might go negative, but it's all positive things here. So it's not going to go negative. It's going to go something like this. Okay, now notice what's going to happen here. If we look for, as y goes to 0, if we look at smaller and smaller values of y, but with t close to x, notice what's going to happen. If t is close to x, x minus t squared is going to be small. If y is small, y squared is small. So if we are close, as t goes to x and as y goes to 0, the denominator here is going to go to 0. And this y is going to 0 slower than this y. So what we end up with, this y is going to 0, slower than this y. And so what we end up with, as t goes to x and as y goes to 0, we're going to get something peakier and peakier, peakier and peakier. So for smaller and smaller values of y, we're going to get something that's even peakier near x here. It's something like this. Okay, and so as as y goes to 0, we're going to get a function that's more and more concentrated around this x variable, around the x. The other thing that I probably should have mentioned first, but I didn't, you should do this exercise. I'm not going to do it, but you should do it. I've actually already done it for one class today, but you guys can do this on your own. So this is x minus t squared. It was an undergraduate class that I did it for. So that's why I'm not doing it for you. It's not because I don't like you as much. This integral, for every x and for every y, this is always equal to 1. Okay, so what happens is we're going to get a function that is peakier and peakier and peakier. As y goes to 0, the function becomes peakier and peakier and peakier. It becomes more concentrated at x equals 0, and if at t equals x, and for t moving away from x, it goes to 0. Okay, so what this says then, py of xt, I want you to think about what its limit is going to be as y goes to 0. Pause and think about it. Okay, so hopefully you paused and thought about it. This is going to go to the Dirac distribution. And that's exactly what item number 2 there says. And I want you to think about it. I haven't proven this, okay? None of this is a proof of this fact. These are just sort of pictorial reasonings for why this should be true. But really, you should graph this in Desmos and see what happens as y goes to 0. Okay. So now I'm going to prove this fact right here. So I'm going to prove this fact. What I need to show is I want to show this limit is equal to f of x. So I need to show that for all epsilon greater than 0, there exists a delta greater than 0, such that if y is less than delta, then the absolute value of u of xy minus f of x is less than epsilon. That's exactly what it means for this limit. By definition, this limit means what I just wrote here. Okay, so what we're going to do is we're going to start by fix epsilon greater than 0. So fix some epsilon greater than 0. And we're going to choose delta to be successively smaller numbers here. That's the there's going to be several estimates that we need to do. Okay, so fix epsilon greater than 0. So what I want to do is the following. I'm going to do this little computation, then I'm going to write something down. And then I'm going to pick my first value of delta. So notice if I look at this integral here, I'm going to write this as 1 over the square root of pi from t equals minus the square root of delta. I haven't told you what delta is yet, but this works for any positive delta. T going from minus the square root of delta to the square root of delta. F of t, then we're going to get y over x minus t squared plus y squared dt. And actually, let me pause here instead of making the change later. I'm only going to prove this for x equals 0. So I'm going to make this modification here. I'm only going to prove it for x equals 0. And then I want you to figure out how to make this proof for a generic value of x. Sorry about that. So I'm going to prove this. I'm only going to prove this for x equals 0. So this is just going to be t squared. Sorry about that. Okay. So hold on a second. I have. I'm skipping ahead here. It's because I just did this lecture, or a very similar lecture, for my undergraduate class, and I'm forgetting which step that I'm on here. Okay, so what I want to do, so I want to show that this is less than epsilon. What I want to do is I want to show that 1 over pi times the integral t equals minus infinity to positive infinity f of t y over t squared plus y squared dt, and I'm going to subtract off f of 0. I want to show that in absolute values, this is less than epsilon. Okay, I'll put the absolute values back in a minute. Now, because I know the integral of the Poisson kernel is 1, I can just multiply this by 1, but my 1 is going to be a tricky one. It's going to be 1 over the square root of pi times the integral t going from minus infinity to positive infinity f of t y over t squared plus y squared dt. Sorry, I did not mean to write the f of t there. Sorry. This integral right here is equal to 1. So f of 0 times 1, this is 1, everything goes okay. Now, f is a constant, f of 0 is a constant, so I can move it on the integral here, and on the inside of the integral. Well, now it's f of t times this function, f of 0 times that same function, so I can just combine this into one integral. And when we do that, we get the following. We get f of t minus f of 0 times y over t squared plus y squared dt. Okay, now what I want to do is I want to show as y goes to 0, this integral goes to 0. Now if you think about the shape of the Poisson kernel, okay, as y goes to 0, if I look at, everything is centered at 0, okay? The Poisson kernel is centered at 0 here. As t goes to 0, as I move away from, as t moves away from 0, and as y goes to 0, that function gets smaller, faster and faster and faster. So outside of a small interval around 0, the Poisson kernel is going to 0. Okay, now near 0, the Poisson kernel is getting bigger and bigger and bigger, but there's two good things. One, its integral is only equal to 1, okay? And 2, I know that f of t minus f of 0, if t is close to 0, f of t minus f of 0 has to be small because f is continuous. So here's what I'm going to do. For all epsilon, okay, so if I have an epsilon, I'm going to choose an epsilon in the following way. So this is obviously not how you write a proof, okay? But look in the notes for the way to write this, but I'm on a board, so I explain it differently on a board than when I'm writing it. But we want to choose delta prime. We're gonna have a delta, like a delta double prime and a delta triple prime, and the smallest one of those will be delta. So delta prime such that if the absolute value of t is less than the square root of delta, then the absolute value of f of t minus f of 0 is less than epsilon over 3. Okay, so what we're going to do is we're going to break this integral up into 3 pieces. We're going to break it up, one integral going from t equals minus delta to delta, plus an integral t going from minus infinity to minus delta, square root of delta here, square root of delta there, square root of delta there, and then plus an integral going from the square root of delta to positive infinity. We're going to make, and then I'm not writing this function, but in each one of these is this function we're integrating. There's obviously not enough room for me to write. What I'm going to do is I'm going to show each one of these integrals is less than epsilon over 3, and when we add them together, it's going to be epsilon over 3 plus epsilon over 3 plus epsilon over 3, which is equal to epsilon. Okay, so let's look at this first integral, the one going from minus the square root of delta to the square root of delta. Okay, so if I just look at this, and t goes from minus the square root of delta, if t goes from minus the square root of delta to the square root of delta, if t goes from minus the square root of delta to the square root of delta, well, the absolute value of this is going to be less than or equal to 1 over pi times the integral t going from minus the square root of delta to the square root of delta times the absolute value of f of t minus f of 0 times y over t squared plus y squared dt. Really should say less than or equal there, but f of t minus f of 0, notice that the absolute value of t is less than the square root of delta, because t is only going from minus square root of delta to square root of delta. So this means that the absolute value of f of t minus f of 0 is less than or equal to epsilon over 3. Now here we're about to use two crucial properties of the Poisson kernel. Number one, it's positive. So its integral over a smaller interval is less than or equal to its integral over a larger interval. So this is less than or equal to, if I replace this with minus infinity to positive infinity. If you remember, we looked at the sine in x over x functions when we looked at the inverse Fourier transform. This is not true. Like if we had sine x over x or sine in x over x, we could not make a similar estimate as n goes to infinity. For two reasons. One, it's not positive, and the next thing that we know, the next important property about the Poisson kernel is that this integral is equal to 1. Well, without the epsilon over 3, this integral is equal to 1. And so this is equal to epsilon over 3. Okay, so we're looking at the square root of delta. If the square root of delta is chosen such that, if delta is chosen such that the absolute value of f of t minus f of 0 is less than epsilon over 3, so the absolute value of t less than the square root of delta, then this first integral is going to be less than epsilon over 3, which is what we wanted. Okay, so that's our delta prime. All right. Now we're going to look at the other two integrals. We have one integral going from minus infinity to minus the square root of delta, and another integral that goes from the square root of delta to positive infinity. I'm going to do this one, and then you can see what happens. Excuse me. I'm going to do this one, and then you can see what's going to happen, or you can try to do a similar estimate for the one going from minus infinity to minus the square root of delta. Okay, so what's going to happen here, the intuition here, is that as y goes to 0, this kernel goes to 0, and so overall this integral is going to go to 0. That's the idea. But it's not just that this integral it's not just that this function goes to 0, it's that it's an integrable function and that function goes to 0. So essentially what we're just looking at is the tail end of an integrable function, and the tail end of an integrable function, that integral should go to 0. Okay. Think through what I just said. I'm using maybe some terms and some lines of reasoning that you're not completely familiar with, but please pause and think about what I'm saying. Okay. So now what's going to happen here? So when we did the integral near delta, we used the fact that the Poisson kernel was integrable, but that I can make f of t minus f of 0 small. Now as t goes to infinity, I can't make f of t minus f of 0 small, but I do know the following. Let me write it down here. Since f is bounded, there is some m such that f of t is less than or equal to m for all values of t. So then what that tells me is this is going to be less than or equal to 1 over pi times the integral t equals minus infinity to positive infinity. Well, if f is less than or equal to m for all values of t, f of t minus f of 0 is less than or equal to 2m. So this is less than or equal to 2m. This is square root of delta to positive infinity. So this is going to be y over t squared plus y squared dt. Okay, now this 2m can come outside of the integral. So it's going to be equal to this. I'm just going to shift this over. Hold on a second. Okay. I'm just going to shift this over, so it's going to be y over t squared plus y squared dt. Okay, but happily, we can do this integral. We can just write out it explicitly. Sorry, there should be a 2 in here. We can just write out what this integral is explicitly. So this is equal to 2m over pi. And if you did the exercise to show that the integral of the Poisson kernel is always equal to 1, this will be no surprise, though maybe you are surprised when I'm writing it arctan there. So pi over 2. So it's pi over 2 minus arctan, and now I just made this whole thing about how you will know what it is, but now once again I'm losing confidence. Where did I put? Yes, okay. Square root of delta over y. Okay, now we're going to choose. Remember, y is going to be. We haven't chosen delta yet, but we're working on choosing delta. Delta is going to be at least smaller than delta prime here. Okay, but we know that y is less than delta, but I can write delta as the square root of delta times the square root of delta, and so this shows me that the square root of delta divided by y. If I divide y by both sides, it says the square root of delta over y, which is what I have over there, is greater than 1 over the square root of delta. Now, since arctan is an increasing function, this tells me that arctan of the square root of delta over y is greater than arctan of 1 over the square root of delta. So that doesn't involve y here. And if I multiply this inequality by minus 1, I get minus this is less than minus that. Okay, but arctan of the square root of delta over y, that's what I have there with a minus sign. So overall, what it tells me is that this quantity here is less than this quantity. If I do this 1 over the square root of delta. Okay, so now delta prime, we'll call it delta double prime. Choose delta double prime such that pi over 2 minus arctan of 1 over the square root of delta. Okay, let's see what's happening. 1 over the square root of delta prime here. Okay, so let's see what's happening here. As delta goes to 0, 1 over the square root of delta goes to positive infinity, and so arctan of 1 over the square root of delta goes to pi over 2, so this goes to 0. Okay, so we want to choose this such that this, choose delta prime such that this is less than epsilon times 3 pi over 2n. Okay, so choose delta double prime such that this is true. So let me just remind you what we had here before. Before we had this, we had the square root. We had the square root of delta over y. Okay, so now let me say up here delta equals the minimum of delta and delta double prime. Okay, so now the square root of delta over y, since y is less than delta, this says that the square root of delta over y is greater than 1 over the square root of delta, which says that minus arctan of the square root of delta over y is less than this. So in other words, I can replace this with 1 over the square root of delta. And now delta double prime was chosen such that this is less than that, but delta is less than delta double prime, or less than or equal to delta double prime. So that same inequality works with delta instead of delta double prime. And so this is less than 2m over pi times this thing right here, epsilon, sorry, it should be epsilon pi over 3 times 2. So this is epsilon pi over 3 times 2 times m. Sorry, I wrote a 3 here. The problem is the epsilons and the 3's. Okay, so the pi's are going to cancel, the m's are going to cancel, the 2's are going to cancel, and this is equal to epsilon over 3. Okay, so then what this shows us is that the integral from minus square root of delta to square root of delta is less than epsilon over 3. The integral from square root of delta to infinity is less than epsilon over 3. And it's just a symmetric argument. It's symmetric, the argument is symmetric from minus infinity to minus the square root of delta. That's less than epsilon over 3. So the sum of them is less than epsilon. Okay, I get that was a lot. I did that fast. But if you want to understand this, you're just going to have to kind of work through and understand all of these estimates. But this is a very typical, sort of a classical thing to show, and that's one of the reasons that I wanted to show this to you guys.